Welcome back to Potentials, where we explore quantum frontiers, consciousness, geometry, and the deeper layers of reality. Today, we revisit the fascinating realm of time crystals, those exotic phases of matter that beat in rhythm through time, but this time with new groundbreaking research that pushes the story forward. You may remember we covered time crystals before, matter that breaks time translation symmetry, repeating in time instead of just space. Well, the quantum frontier just moved. Researchers at Aalto University in Finland have for the first time connected a time crystal to an external system, thereby opening up new pathways for quantum sensing and memory. Let's unpack what they just did, why it matters, and what it might mean for future technologies, and yes, for our broader view of reality. Quick refresher: a time crystal has atoms arranged in a repeating spatial pattern. A time crystal, in contrast, has a system whose lowest energy state is one where there is periodic motion in time. The system spontaneously breaks time translation symmetry. First proposed by Nobel laureate Frank Wilczek in 2012. Early experiments in driven Floquent systems, then continuous time crystals, etc. The key takeaway: these are not just curiosities. They open up possibilities for ultra-stable time reference, quantum memory, sensing, and so on. Here's what's new. The team used a superfluid of helium-3 at near absolute zero, injected magnons, magnetic quasiparticles, via radio waves. When the pump turned off, the magnons self-organized into a continuous time crystal that lasted up to over 10 cycles, several minutes before fading. Crucially, during the decay fading phase, the time crystal connected to a nearby mechanical oscillator, a surface gravity wave mode on the liquid helium. The coupling was controlled by the oscillator's frequency and amplitude. They found the time crystal's frequency shifts behaved analogously, I cannot say this word, to optomechanical systems where optical cavities interact with mechanical oscillators. That means the time crystal can be manipulated or tuned via an external system, a significant shift from prior experiments, which kept time crystals isolated. The implications: because time crystals last for orders of magnitude longer than quantum systems currently used in quantum computing, they could serve as memory systems or ultra-stable clocks, references in quantum devices. Why this matters? Let's translate that into broader terms. From isolation to interference. Historically, time crystals were isolated so as not to disturb the quantum coherence. Here we have coupling, which offers control and integration with external systems. New technological possibilities. Think quantum memory that is super stable, ultra long-lived. Think sensors that measure minute changes in time frequency by harnessing the intrinsic periodicity of a time crystal. Think frequency combs derived from time crystals. Bridge between quantum and classical domains. Optomechanics lives at the boundary between quantum mechanical motion and macroscopic mechanical motion. By showing time crystals can function similarly, we're seeing new hybrid domain. Metaphorically, for consciousness/time/geometry, if matter can crystallize in time and then engage with external systems, it invites reflection. Is our consciousness an emergent time crystal-like state interacting with the world? Is the universe doing temporal crystallization of information? The big picture and the future questions are, here are some open questions and speculative vistas. How far can the coupling be pushed? Right now, the coupling strength is weak. The team suggests replacing the large liquid surface with nanoscale mechanical resonators to reach the quantum regime. Could room temperature analogs or more practical materials host time crystals with similar coupling? The paper speculates about YIG films hosting magnon-based time crystals. What happens when the time crystal is used in a quantum memory or frequency reference? Could we harness the repetitive motion in time for storing quantum bits or timing signals with unprecedented stability? On the philosophical side, a time crystal challenges our conventional view of static ground states. It says, even in lowest energy, motion persists. What does this teach us about the nature of rest, stability, change, and time itself? To sum up, the latest research on time crystals opens a new chapter, from isolated quantum curiosity to integrable quantum technology. If we can harness the rhythmic heartbeat of a time crystal and couple it with the world, the doors will open to new quantum devices, new timing systems, new layers of measurement. If you enjoyed this dive, hit subscribe, leave a comment, tell me what you think. Do you believe time crystals might play a role in future quantum computers, in the fabric of consciousness? And I'd love to know if you want a deeper episode purely on the geometry and the poetry of time crystals. Thanks for listening. Until next time, stay in rhythm, stay curious, and stay crystalline.